All right, so today we're going to complete this picture of co-state estimation using pseudospectral methods. Today we're going to talk about co-state estimation using collocation at LGL points. This is the last of the three. Now, what I want you to, after we're done with this, I'm going to go through some other details, but let's go back. Remember in the LGL method, so let tau 1 through tau n be the LGL points, or the Legendre-Gauss-Lobato points. Now in this case, we know that tau 1 is equal to -1 and tau n is equal to +1. So that's really important that we establish that, because the points now include both endpoints. So if you remember that in the LGL method, the state is approximated as follows. We've got x of tau is equal to the sum from I equals 1 to n of xi li of tau, where in this case the Lagrange polynomials are equal to the product j equals 1 up to n, j is not equal to I, tau minus tau j all divided by tau I minus tau j. And this is for I going from 1 up to n. Right now remember that this is a polynomial of degree n minus 1. And when we differentiate it, so I should complete this picture here, x of tau is approximated as that. So x dot of tau is going to be approximated by capital X dot of tau, which is going to equal the sum from I equals 1 to n of xi li dot of tau. Now, if you look at that, you see that, again, that's a polynomial. The original state approximation is a polynomial of degree n minus 1. So this is a polynomial of degree n minus 2. So then we collocate x dot of tau at the n LGL points to give the following, which is that x dot of tau j, which is equal to the sum from I equals 1 to n of xi li dot of tau j, is equal to f of xj uj. And this goes j equals 1 up to n. Now, if you look at that, you see that now we're collocating a polynomial of degree n minus 2 at n points. And as I mentioned before, polynomial of degree n minus 2 is uniquely determined by n minus 1 coefficients. So we're over-collocated. But nevertheless, the goal here is to go through co-state estimation. So we're gonna do this. Now, the equation, so the NLP, the NLP arising from LGL collocation is the following, is that we're going to minimize phi of xn subject to the constraints that f1 colon n minus d x1 colon n is equal to 0, and x1 is equal to x0. Now, that's all pretty straightforward. What we're going to do now is we're going to formulate the KKT conditions of this NLP, just like we did with Gauss and with Redau. We're going to do the same thing here. So what we do is follows, is that the Lagrangian of the LGL NLP is the following. It's L is equal to, now we got to put all these things together. We've got the cost function, right, plus the inner product of these multipliers now, lambda 1 through n, with f1 colon n minus dx1 colon n. And then we get plus the inner product of mu with x1 minus x0. Okay? So that just takes care of all the terms. No, actually, sorry. I've got to be consistent with my conventions here. So this is x0 minus x1. So now if we take the derivative, you notice the NLP variables are x1 to xn, which are the row vectors that represent the state at the n LGL points, and u1 up to un. Okay. So if we take the KKT conditions of this, so we take the first derivatives with respect to all the variables, what we wind up with is as follows. Is the first order optimality conditions of the LGL NLP look like this. So now you'll see here that the initial value of the state, which is that capital X1, actually appears in two places. It appears in this middle term and it appears in this term. And that the final value appears in the first term and the second term. So we're going to have to deal with the initial and final values separately from the interior values. So the first thing we do is we get the gradient with respect to x of lambda 1. So I'm going to deal with the first point. And then I've got f of x1 u1 has minus d1 transpose lambda 1 colon n is equal to mu. So that takes care of the initial point. Now I'm going to do the final point, which is dn transpose times lambda 1 colon n. You notice that lambda 1 colon n keeps appearing here, minus the gradient with respect to x, lambda n, with f of xn and un. This is equal to the gradient with respect to x of phi of xn. And then I've got the middle terms, which are the gradient with respect to x of the inner product of lambda 2 colon n plus 1 with f 2 colon n plus 1 is equal to d 2 colon n plus 1, or n minus 1. So these are 2 to n minus 1, I'm sorry. Minus 1. Transpose times lambda 2 to n minus 1. And then the last condition is that the gradient with respect to u of lambda 1 colon n times f 1 colon n has to equal 0. Now you'll see this first condition, if I take the derivative with respect to x1, I get these three terms, right? I get this first term because I get the derivative here with respect to x1, which is that. I get the derivative over here with respect to x1, which is this. And you'll see that just winds up. And then you get the derivative. So you've got the derivative in a few different places, right? Because this is a function, f1 colon n is a function of f1, and then x1 colon n is also a function of x1. So I've got those two terms. And then the derivative here, the derivative with respect to x1 just gives me the mu. And the same thing happens with all the other terms that you see in the rest of the equation. So now what we're going to do is, in a manner similar to what we did with Gauss and Redau, we're going to define another matrix, which allows us to transform the multipliers accordingly. So what we're going to do is we're going to say let the following be true. Lambda 1 through n is going to equal W inverse times lambda 1 colon n. Remember, lambda 1 colon n, the capital lambda 1 colon n, are the Lagrange multipliers associated with those collocation equations. And these little lambdas, these are the costate estimates at the n LGL points. So now what we're going to do is we're going to say And we're going to define the following matrix. And let D dagger be another matrix of size n by n such that the following is true. D11 dagger, or I should be more explicit, DII dagger is equal to DII, and then D11 dagger is equal to minus D11 minus 1 over W1, and then DNN dagger is equal to minus DNN plus 1 over Wn. And then finally, Dij dagger is equal to minus Wj over Wi Dji. And then this is for I and j equals 1 up to n, but I is not equal to j. Okay? So that takes care of all this. Now, what we're going to do is we're going to use all this information and we're going to put it together such that we're going to rewrite these equations in terms of D dagger. So if you write everything in terms of D dagger, what you wind up getting is you get this. So I'm going to collapse all these into as few equations as I can. And the way I'm going to do that is as follows. I'm going to say let E1 and En be the first and last columns of the n by n identity matrix. So by doing that, we can actually collapse these three equations into a single equation. And that single equation looks like this. So in terms of D dagger, we obtain the following result, which is that D dagger lambda 1 colon n is equal to minus the gradient with respect to x of lambda 1 colon n with f 1 colon n. But now we've got these two terms that come in from the first and last columns of the identity matrix. And then I've got plus En all divided by Wn times lambda n minus gradient with respect to x of phi of x n. And then, of course, you've still got the other expression, which doesn't change, which is that let me erase this down here, which is that the gradient with respect to u of lambda 1 colon n with f 1 colon n has to equal 0. But if you remember, that can be rewritten as lambda 1 colon n can be written as the weight matrix. So you can factor the weight matrix out of this whole thing. So you just get lambda 1 colon n, little lambda 1 colon n, f 1 colon n is equal to 0. So if you look at this expression, you'll actually see that there's a bit of a problem here, right? If I didn't have the E1 and the En, then what this would look like is it would look like the derivative of the costate is equal to negative of the Hamiltonian, because lambda transpose times f, which is what this is essentially the Hamiltonian in this case, because we just have a Mayer cost. So this becomes minus dh dx. But I don't get lambda dot is equal to minus dh dx. I get lambda dot is equal to minus dh dx plus two additional terms. These additional terms are the transversality conditions in the NLP, right? I mean, this transversality condition is at the initial point. This one's at the final point. This one doesn't tell me anything, really, because I don't know mu any more than I know lambda 1. But the last one is the transversality condition on the final on the final state. So what happens in the case of Lobato is that, I'm going to write this down. In the case of Lobato, case of LGL collocation, the boundary conditions are coupled to the approximation of the costate dynamics. Now, you remember that in the case of Gauss, the boundary conditions were actually completely decoupled from the costate dynamics. In the case of Radow, one of the boundary conditions, which is the initial condition, was still coupled. But what you'll actually see when you do the calculations is when you try to estimate the costates, that using these transformations, because Gauss and Radow are both implicit integration schemes, whereas Lobato is not an implicit integration scheme because the D matrix for Lobato is singular, you wind up seeing that there's a null space that comes into the costate estimate in over here. And when you actually compute the costates, you'll actually see that a lot of times, for many problems, that the costate estimate isn't very accurate. So just to summarize, let's just summarize all this now. So we've got 3 sets of costate estimates. So I'm going to write them all down because the whole point to this is to make your life easier. It's not to make your life harder. So summary of costate estimation using LG, LGR, and LGL points. Okay, now let's go through this, okay? So here's our summary, which is 1, LG collocation. Now, if you remember, in the case of LG collocation, I actually have to write all this down, so let's go through it, which is that the costate at the Gauss points, because remember 1 through n always represents the collocation points, so in this case that's the Gauss points. We get W inverse, which is the inverse of a diagonal matrix of Gauss weights, times lambda 1 colon n, plus a column vector of 1s times the Lagrange multiplier at the final point. This is the Lagrange multiplier associated with the quadrature equation, right? And then lambda n plus 1, which is the costate estimate at the final point, is just equal to the Lagrange multiplier at the final point. And then we wind up with the other result, which is that the costate at the initial point is actually computable as follows. If I still have it. Let's see here. Still have that result. Yes. So lambda 0 is equal to lambda n plus 1 minus W transpose times D times, well, let's see here, minus the sum from I equals 1 up to n of d I n plus 1, so this is the last column of the D matrix, times lambda I, which is equal to lambda n plus 1, well, let's keep it in terms of big lambda, lambda n plus 1 minus d n plus 1 transpose times lambda 1 colon n. So this is the initial costate estimate. So you can see that this gives you a transformation. So I start with the KKT multipliers of the NLP, and I get a transformation that takes me to the costates of the optimal control problem at the Gauss points and the boundary points, because lambda n plus 1 is the final point, lambda 0 is the initial point. In the case of Radow, the result is a little bit simpler, which is that, so if I do LGR collocation, I wind up with the following result for LGR collocation, So, which is that you get lambda 1 colon n is equal to W inverse lambda 1 colon n. Now, in this case, 1 through n are the LGR points. And then you get lambda n plus 1 is equal to dn plus 1 transpose times lambda 1 colon n. So this is actually a really nice result because it's simpler than the result for Gauss. And as you'll see, if you actually compute a solution with it, it's actually quite accurate. For LGL collocation, you actually get an even simpler result, but you'll actually see that if you actually play this out in practice, it actually turns out that the result isn't very accurate. Now, I did all this for a problem where we had a Mayer cost and we only had the time interval from -1 to 1. Now what we're going to do is nothing fundamentally changes with any of these costate estimates. They remain exactly the same in the case of a more general problem. So let's go to a more general NLP, more general optimal control problem. So and I'm not gonna derive all the results because, like I said, the costate estimates stay exactly the same. So, but what I'm going to do is I'm just going to show you how the discretization plays out. So when you get a problem where the time interval is not -1 to 1, or you have a Lagrange cost, you can actually do this. So in the more general Bolzа problem, right, what we had was the cost functional was phi, which was a function of x of t0, x of tf and tf, plus the integral from t0 to tf of L of x of t, u of t, and t dt. So that's what we were trying to minimize. And the dynamics were x dot is equal to f of x of t, u of t, and t. And then we had boundary conditions, phi, which is a function of x of t0, x of tf, and tf, which were equal to 0. And then we might have some path constraints, which were c of x of t, u of t, and t were between some c min and c max. Now, this is actually very easy to discretize using any of these pseudospectral schemes. Let's start. I'm going to do this for Radau first, all right? So let's discretize that problem using Radau. So discretize Bolzа problem using LGR collocation. So the way we have to do this is we first have to transform the interval from t0 to tf to -1 to 1. So we know that t lies between t0 and tf. So that means that 0 is less than or equal to t minus t0 is less than or equal to tf minus t0. Now, tf and t0 themselves may actually be variables. They may not. They don't have to be fixed values. They could actually be parameters in your problem, which says that 0 is less than or equal to t minus t0 all divided by tf minus t0, which is less than or equal to 1, which says that 0 is less than or equal to 2 times t minus t0 over tf minus t0, which is less than or equal to 2, which says that -1 is less than or equal to 2 times t minus t0 all divided by tf minus t0, which is less than or equal to 1. So basically what I can do, -1 is less than or equal to 1. So I can define this quantity right here. I can define this to be tau, right? Now, if I define that quantity to be tau, then the next step, erase all this stuff. All right, well, we'll erase it, okay? So, because I can remember all these, it's not really a big deal. Let's look at this now. So if I define tau to equal to t minus t0 all divided by tf minus t0 minus 1. Then what you can see is you can see that d tau dt is equal to 2 over tf minus t0, which implies that dt, d tau, is equal to tf minus t0 over 2. So we can discretize each of these now, which is that x of t0 goes to x of minus 1 when I'm in tau. X of tf becomes x of plus 1. And what we also get is that the integral from t0 to tf of, say, some arbitrary function f of t dt, right, is going to equal tf minus t0 over 2 times the integral from minus 1 to 1 of what? F of tau d tau. And that comes from the fact that if I look at this, you see that dt is equal to d tau times tf minus t0 over 2. So I just did a substitution in there, right? So then I can remap this problem quite straightforwardly to negative 1 to 1, which is the same problem. It's just I've just transformed it to negative 1 to 1. So on tau in negative 1 to plus 1, we have the following, which is j becomes phi of x of minus 1 t0, x of plus 1 tf, plus tf minus t0 over 2 times the integral from negative 1 to 1, L of x of tau, u of tau, and tau, but now I've introduced these parameters t0 and tf, so this becomes a function of t0 and tf, d tau. And now my dynamics, because if I take dx dt, the original dynamics are dx dt equals f of x, u, and t. If I differentiate that, dx dt is equal to dx d tau times d tau dt, but d tau dt is 2 over tf minus t0. So what I get is dx d tau is equal to tf minus t0 over 2 times f of x of tau, u of tau, and tau. But again, I've introduced parameters t0 and tf into this problem. I've got the boundary conditions, phi, which are now a function of x of negative 1, t0, x of plus 1, tf. That has to equal 0. And then my path constraint becomes c of x of tau, u of tau, tau, t0, and tf are between c min and c max. But if you look at that problem is basically the same complexity as the problem we started with that Mayer problem, because now everything's defined on negative 1 to plus 1. So let's suppose I do this with LGR collocation now, right? So all integrals get replaced by whatever the quadrature rule is that I'm using. So if we do LGR collocation, what we get is j gets approximated by this thing I'll call jn, which is, when I discretize using endpoints. I get phi of x1, right? Because that's the initial state, t0, x n plus 1, because that's the final state, tf, plus tf minus t0 over 2. But now I'm approximating a quadrature. So I'm going to get the quadrature, which is the sum from I equals 1 to n, L, which is now a function of xi, ui, tau I, t0, and tf, right? Well, sorry, I forgot the weight. Put the weight in there. The sum from I equals 1 to n, wi, because I'm approximating with a Redal quadrature. So that takes care of the cost. The dynamics get approximated by d times x, 1 through n plus 1, is equal to tf minus t0 over 2 times f of x 1 colon n, u 1 colon n, which we've defined already to be f1 colon n, which I defined before. And then my boundary conditions, phi becomes a function of x1 and then t0, xn plus 1, and tf, right? And that has to equal 0. And then the last one is that c min less than or equal to c of x of tau, which is x1 colon n, and then u of 1 colon n, and then tau 1 colon n, and then t0 and tf less than or equal to c max. Now, if you don't like the way I wrote that, because that's sort of in a vectorized manner, we could also write it this way. We could write it as c min, because really this is kind of an abusive notation. It's less than or equal to c of xi, ui, tau I, t0 and tf less than or equal to c max, and this is for I equals 1 all the way up to n. All right? So let's look at this problem. I mean, there's nothing fundamentally different about this problem from the one I did earlier, the Mayer problem, except for the fact that now I've got these scale factors of tf minus t0 over 2. So let's suppose we had a problem where the interval was actually negative 1 to 1, where t0 was negative 1 and tf were positive 1. Or it could be anything. It could be 0 to 2. But basically, tf is 2 units larger than t0. So if tf is 2 units larger than t0, you can see that tf minus t0 over 2 is always going to wind up giving you 1. So that's the problem that I did initially, which was the problem on negative 1 to 1. So by transforming from tf minus t0 to, t0 to tf to negative 1 to 1, all I've done is introduce the scaling factor of tf minus t0 over 2. So fundamentally, I really haven't done anything that new, except for the fact that both tf and t0 could be parameters in the problem, as well as now everything can vary. The initial state could vary, and the final state could vary too. In the problem that I did before, the initial state was assumed to be fixed at a value x at negative 1 equals x0, but that there's no reason that has to be the case. I can actually allow it to vary, and I can just stick it into the boundary conditions. And you're going to get a similar result if you do this for Gauss or if you do this with Redau. The difference with Gauss, of course, is that you, in addition to having this equation here, which defines the discretization of the dynamics, you also have the quadrature equation. In the case of Lobato, you get something that looks almost exactly the same as Redau. So what we've done in these last few lectures is we've come up with a way of being able to estimate costates using collocation at 3 different sets of points. They all come from Gaussian quadrature nodes. The first one is Legendre-Gauss, the second one is Legendre-Gauss-Redau, and the third one is Legendre-Gauss-Lobato. All 3 of these are high-accuracy Gaussian quadrature rules, the difference being how the endpoints are dealt with. The endpoints in Gauss are dealt with by introducing 2 new non-collocated points in addition to the n Gauss points that are tau 0 and tau n plus 1, which give you the values at tau equals negative 1 and tau equals plus 1. In the case of Redau, we had to introduce 1 non-collocated point at the endpoint because the Redau points include negative 1. And in the case of LGL, we see that the LGL points already include both endpoints. The key thing, though, is that when I derived the original methods, I explained that the differentiation matrices using Gauss and Redau were rectangular. They were not square, and they were not square in such a way that if you lopped off the first column of either of those matrices, you were left over with a square matrix that was invertible, and the inverse was the Gauss integration matrix or the Redau integration matrix. In the case of Lobato, the matrix was square, and it was singular because we had a polynomial of 1 higher degree one lower degree than the number of points that we needed to approximate that polynomial exactly. In the case of Lobato, we had a polynomial of degree n minus 1. We collocated its derivative at the n Lobato points, but its derivative was a polynomial of degree n minus 2, and a polynomial of degree n minus 2 is uniquely defined from n minus 1 coefficients, but we had n coefficients, so the system that we got led to this singular differentiation matrix. That singular differentiation matrix, then, since it can't be inverted, there is no equivalent integration approximation or quadrature approximation to the differential form. So the differential form for Lobato is singular, whereas the differential form for Gauss and Radau had this inverse relationship where there actually was an integral formulation that was identical to the differential formulation. So even though Gauss and Radau are differentiation methods, they're differentiation methods that have an equivalent integral form. So in fact, they are integration methods, even though we don't write them that way. Now, what I've done today, after getting through the Lobato costate estimation, is I've explained that the methodology that I wrote down for that simplified Mayer problem, I just did it for LGR. This should say LGR. Apologize for this. This is LGR, which is that the method. I wrote it down for LGR collocation, but you get a similar form for LG and LGL. The only difference is the fact that you have to introduce the quadrature equation in the case of LG, and then in LGL you get this exact same equation for the dynamics, except for you have to realize that the matrix in LGL is square as compared to that for LGR, which is rectangular. So I'm going to stop with this right here because the rest of this then gets into things like implementation and how you actually set these problems up on a computer. That doesn't really work very well on a board. So we're going to do that, afterwards. And the better way to do that really is to have you come to my office and discuss it with me so that we can go over these things in a logical way, because a lot of the implementation issues are things that I can't really cover implementation in class in any kind of a systematic way. I can give you some tips, but it doesn't really constitute a sort of a lecture on sort of the pedagogy of this stuff. It's more of a just a practical kind of thing. Well, which is important too, but I think that's better done if you actually come to my office and discuss it with me. So anyway, for right now, we're gonna sort of take a break here from this, and when we come back with the next lectures that we're going to do, we're going to go back to some of the theory, and we're going to start talking about things like inequality path constraints and how to deal with inequality path constraints in the theory, and because I haven't really discussed much up to this point with path constraints. So that's it for today.